start the afternoon session with Boris Saavedra on a simple simulation of the IceCube neutrino telescope.
Okay. First of all, I would like to thank to the organizers for giving me the opportunity to show this this idea here in the Andes workshop. I'm saying this very honestly because this is by far not a fancy idea, but it's mostly a very simple idea that appeared to me after looking for an answer to the question about how could I try to contribute to the development of Andes or to do something about. I have been following the experiment since I think it started, but I haven't been able to do something to really contribute. So maybe this is just a first step, I don't know. Let's see, so the idea is the following, it's very simple. I would like to call the attention, because I suppose that you don't need to be convinced about this, about the one part of the computations that could be useful in this stage of the endeavor. And I'm talking about the simulations of the experiments that we are normally discussing about for Andes. In order to strong this idea, I divided the talk in three parts. So what is it? Okay. In the first part, I would like to just highlight some motivations, general motivations, to study experiment simulations in general and specifically for Andes, and what are the kind of computations that we normally see in current papers that talk about these prospects for Andes. In the second part, I would like to show you what I understand for a simulation, because this is a very broad concept, right? For sure, there are more sophisticated ways to approach to this problem, but and this is quite simple, but with the benefit that is developed through works that I have done. Okay, so I have some control about them. And in that step, I would like to show you a proof of concept of this way of seeing the experiment simulations, by describing a little bit my work in considering the experiment simulation of the IceCube telescope. That is a huge neutrino telescope that could look similarly to the kind of Andes neutrino detector that we have been discussing so far. So let me start with a little bit of introduction. So the introduction is very general, it's quite simple. And it's trying to call the attention about the following things. So, in general, normally if you look at the HPH papers, or even in the talks that we have seen today, the subject of experiment simulation is not normally speak, right? It's not normally put it as a first subject to study. But if you look into these papers, or if you ask about how do you get to that kind of the computation that you see in the plots for prospects, exclusion limits, etc., you are going to find in every place the role of experiment simulations, because it's a natural step when you have when you do your research. Normally, when in general, how I see normally how the research evolve is in the following way. Very simplified one. So initially, you have to specify the model to be studied. Normally, beyond the standard model building. I work in phenomenology, and normally this is like the first step. So this is like the creative step. But then afterwards, you have developed your Lagrangian or your specific model. You necessarily need to compute the observables to relate the model to the observable data, right? And that task is sometimes easy, sometimes not so easy, and in general, for the kind of phenomenology that we are talking about and we're thinking for Andes, this kind of computations can get complicated. So in order to systematize this kind of computations, going beyond, I don't know, a Mathematica file or a Maple file, I don't know, to compute these things, maybe it's a good idea to start thinking about a systematic way that I try to put it in the concept of experiment simulation. Because having this kind of approach, then you can do other things, like for example, project the results for future conditions. Normally you do an analysis with current data, you find that your model is not excluded now, but you ask when it's going to be excluded. And for that, in order to do that question, in order to answer that question, you need to extrapolate your prediction of the experiment too. And that can be done naturally if you have a simulation of the experiment, because you just change the parameters and you go forward. Also, it happens that you can suggest new ideas about observables because you know better the machine. Okay, you don't only take the data that you copy paste from the experimental papers, but you can discuss more deeply about the possibilities of the experiments. You also can add things to the simulations in order to see what kind of observable you will need in order to prove some part of your model or some part of your theory. And also, one thing that looks interesting, but it goes beyond what I have done so far, is suggest new experiment with particular properties. So we are thinking about Andes, and normally we see the pictures of the experiments and how they work, but it will be nice at some point, I suppose, to have prototypes of these experiments in the form of simulations in order to have more systematic and more quantitative results apart from the picture. This seems to be a nice time to think about that, I think. I'm not an expert on this kind of simulation approach, but what I have realized is that it could be very useful if you think about experiment simulations when you are thinking about the experiment that you will like to build. I don't know, maybe it's too early, maybe I don't know. But at this point, as far as I know, I haven't been able to find simulations in the market for the Andes experiments. And you have different possibilities. So you can try to work in neutrino detectors or another kind of neutrino detectors, dark matter, or other things that I don't really know, nuclear astrophysics. But normally I am going to be talking about this kind of experiment, these large neutrino detectors. Why? Because they are very similar to IceCube. And IceCube is the beast that I have been working. So, but what also I have been understanding with the time working on this kind of computation is that the system to work on this kind of simulations is very similar for different experiments, apart from the details of each of them. So it's it looks like a very narrow objective to talk about neutrino detectors, but in general, you are gonna, when you do this kind of studies about simulations, you start realizing that the techniques that you are learning can be applied to different situations. So, for instance, what is the current results or status of the computations talking about potential experiments at the Andes site? Okay, for example, you can read this paper where they do an analysis of the potential experiment that you could install in the Andes laboratory, and for example, they use these computations to compare the Andes neutrino detector with the specific properties with other kind of detectors. And for example, here they measure the geoneutrino events for a 3 kiloton liquid scintillator detector operating during a year with 80% efficiency at different locations. And the nice thing of these results are that Andes seems to be quite competitive, at least in this kind of measurement. So, but this kind of number depends on the particular properties of the experiment. For example, the location. In order to compute, to know what are to predict this number, you need to know the features of the location around Andes. So you need some kind of a specialized computation. So looking at this kind of results and the energy that is invested on this endeavor corresponding to Andes, I think that maybe it will be a good idea to go deeper on this kind of computation and develop systematic experiment simulations. And for instance, what are the kind of computations that you can systematize? This is a very simple expression that you can find in this paper too, that compute the number of events, neutrino events, given some flux and some cross-section, the flux of electron antineutrinos and the cross-section of the electron antineutrinos and the proton, and integrated about some energy threshold, okay? This is an observables, and these are the input data. So from this simple expression, that is the one that they used to do the analysis that I was showing previously, you can see that there are different blocks that you need in order to compute these numbers. For example, we have the flux of the neutrino, the detector properties, that here are very simple, like the number of protons in the target, or the energy threshold, the minimum energy threshold, and cross sections that normally are the particle physics part of this kind of computations. So the idea is to systematize this kind of computation. When I mean experiment simulations, it's nothing more than try to do these computations, or more complicated one, in a systematic way. Okay. So let us try to say more, to be a little bit more specific about how we can do this systematization for this very simple example. So, the problem that, as I see it, in order to compute this simulation of a given experiment, it has just 3 steps in general. First of all, you have to look at a particular experiment. For example, this is this is like a figure representing the IceCube volume, and we have here what is IceCube able to measure, that is the interaction of neutrinos with ice, and this interaction then produce electrons and photons that can be measured by the photodetectors. Okay. And from this first abstraction of the experiment, you can pass to some some formulas that give you the first quantitative realization of your experiment. The following step is transform this into some kind of systematic computation, or what I call a simulation. And in order to do that, it's quite simple. You can see the previous equation, and you can split it in these 3 parts, that for this kind of expression are very like literally almost from the expression. So you can see in the incoming flux like an input file, like a TXT file. You can see in the simulation itself as a program that receives this incoming file and generate and do the computation, include the cross section, do the integral in the energy, and finally give you the final number of particles. Okay, this is also an output file that then you can use for your phenomenology or for your study of your prospects. So the idea is to work on this kind of block chain in order to achieve this systematicity that I am talking about. Clearly, the simulation of an experiment can become much more complicated than this. This is just an example, and at the end of the talk, I'm just going to show you a little example of how our program works for the simulation of IceCube. So, and this is the last part of the talk, where I would like to show you that this simple method can be used to do research in this case about phenomenology, this particular experiment that is IceCube. And my goal is to show you the final flux diagram of this experiment. But before, I just would like to recall you about what is IceCube. Maybe not everybody know about this detector, but it's kind of famous. So the IceCube is a neutrino telescope which is able to measure the most energetic neutrinos circulating in the cosmos, which are most probably related to the origin of cosmic rays, but with energy that allow to investigate high energy physics at interesting regime. So the first goal of IceCube is to measure these neutrinos that are produced in the very far from us in the cosmic ray engines like galactic centers and this kind of astrophysical processes. And they have done it very successfully so far. So they have discovered these neutrinos coming from this kind of processes. They have distinguished these neutrinos from atmospheric ones. And the last measurement that they have released that is quite interesting is the measurement of one high energy neutrino from the direction of a blazar. It is its relationship with the production of cosmic rays have been studied by considering a multi-messenger analysis. So basically, this is the first time that they have measured different particles from a particular, a singular object like a blazar, because the underlying processes that generate these neutrinos also generate other kind of final states, like gamma rays and also cosmic rays. Okay, so this is the first time that they have been done this complementary discovery of two different kind of particles, in this case neutrinos and gamma rays, from the same point in the space. And this is one step forward to understand about the origin of cosmic rays. That is an astrophysics endeavor, but is interesting for the whole community. So on the other hand, what I have been more focused is in the property of these neutrinos that are detected on IceCube, that are neutrinos that are so energetic that can cover slightly the electroweak regime. Not above the electroweak regime, but if you consider the center of mass energy of the interaction between neutrinos and protons, you can reach very close to the mass of the weak boson. So in principle, you can analyze high energy physics in this kind of machine. Of course, the luminosity is quite low, and the things that you can do are quite restricted. But in principle, you can verify, for example, some limits that have been put by the LHC, and you can try to see if the measurement that you do in the IceCube are compatible. This is an exercise, but it's in some sense interesting because IceCube is not the kind of machine that you will use to study high energy physics, but it's more related to this kind of cosmic ray. But in principle, you can do that. In this case, in the case of IceCube, the expression that I was showing you before for the model of the neutrino telescope for Andes is a little bit more complicated, and it has this kind of expression. And in general, you have several of these expressions. So here, what you compute is the number of events from a given interaction of a given flavor alpha interacting with through some process X, giving you some topology C that can be showers, tracks, double bank, etc. These are topologies that are defined in the experiment, and that can come from the two different hemispheres. So this computation can give you information about the south and north neutrinos. Okay, so these are kind of more complicated expression than before, but it's something that really needs some systematization in order to be used for the research. And this is what we have been doing during the last years. So what we have done is try to compute these events for IceCube using different levels of approximations for the computations, and it's for me it was like how to say, like a way to understand how these simulations can work, like by doing it by examples. So for example, in our first work, we considered the search of dark matter component on the first data delivered by IceCube in terms of events as a function of energy. Only the energy was the free parameter. And we used approximations, very rough approximation, for example, assuming that the detected energy is equal to the incoming neutrino energy, which is something that is clearly not the most accurate way of seeing at events. But it was the kind of computation that we have available in the beginning. And it was useful to do this research, and the results were I don't know how to say, they were important, interesting. You can see it for yourself. They were accepted for publication. But also, it was one of the first papers looking at this kind of interpretation, but then there were a lot more. But the level of the computation never increased too much. That was something that caught my attention, because in principle, there were many approximations that we did here that could be improved. And for example, we were working in this equality to do it better, to really compute the detected energy in terms of the incoming energy. And so we considered energy reconstruction effects. And also we added some extra information about the topology of the events at the detector. In the beginning, all the events for us were the same kind, just neutrino events. But then we separated this between shower and track topologies. And these kind of topologies are useful because they can identify between different flavors of neutrinos. Electron neutrinos would produce mostly shower depositions of energy in the detector, and muon neutrinos will produce, when they produce muons through charged current interaction, will produce track topologies. So in order to do, when you have that kind of information, plus some trigger condition that we also added, we could analyze some information about the flavor composition of the incoming flux. That is an issue for the IceCube telescope. They are still measuring, the errors are big, and it needs to be studied with some detail. Okay? In a third paper, we have added the possibility to extend the standard model in order to analyze possible beyond the standard model signals at IceCube. So basically, we added the option to compute neutrino-proton interactions, but with other kind of interaction, with beyond the standard model interaction. And the model that we considered for this particular publication was a leptoquark model. But the model itself is not really the matter of discussion, or the most interesting thing for me is the point that it was possible to do this kind of BSM analysis in IceCube, but we discovered at the end, maybe we could have advanced it from the beginning, but just after the computations, we were convinced that the reach of IceCube to do this kind of analysis is obviously below the LHC, but it can work like a complementary revision of the data. That is on the one hand. On the other hand, you could try to find different kind of model beyond the standard model that has some properties that prefer to be measured at IceCube than in the LHC, but we are working on that kind of situation. So along this work, we have also included the computation of north-south spectrum, which can be useful and extended for angular coverage, which is a nice tool to analyze the data from the deep core. The deep core is like the central part of IceCube, which is more densely populated with detectors that allows the detection of low energy neutrinos. So the low energy neutrinos are mostly produced by atmospheric processes, and they offer more statistics. Okay, and the angular dependence can talk about the properties of the matter oscillations, and you can understand, for example, some properties of the air density, because as you move in the angle, you analyze more or less matter traveled by the neutrinos when they arrive from the north, for example, to the IceCube. So it's an interesting way to follow with this simulation and add systematically more features that allow you to do more research. And this is the kind of thing that motivate me to think that this kind of approach could be used to understand or to simulate some kind of experiment at Andes, because you start with something, but you don't really know where you're gonna end. And this is like something that can be pursued coherently by using this kind of simulation, because in the way that I show you that we use this simulation, you normally construct above what you have done before. So you create versions and new versions, including more details. that that if you're lucky can give you some chance to study new things from the theoretical point of view or from the experimental point of view. And the last thing that we have added to the experiment simulation of IceCube is this new topology, that is the double bank topology, that hasn't been measured yet, as far as I know, and but it's going to be useful to distinguish tau neutrinos from mu neutrinos and electron neutrinos. And with that tool, the errors in the determination of the flavor composition of the incoming flux is going to be reduced. And we are trying to implement this extra feature in order to be able to analyze this data, in order to understand possible departure from the standard model or possible departures from the standard incoming flux, etc. I just would like to recall you that the incoming flux has information about the production, okay, about the processes that you have in the beginning of at the source of these neutrinos. So it's really important to measure it from an astrophysical point of view. So this new implementation is in that direction. So finally, I just would like to show you how looks our program in terms of this flux diagram. And it's something that it's something that also allows for thinking about possible extension, new features, and I don't know, things that you can add to the experiment. So basically, you start with this. Okay, the idea of the program that we have developed is that you enter a param card, just following the nomenclature of MATLAB, that is one famous simulation program, but for cross-section computation. So in this param card, you can give the parameters of your initial flux, or you can put an arbitrary flux if you want. You can add beyond the standard model conditions, for example, define the coupling, the mass, and etc. Experimental conditions like the exposure. So you use this input card, and then you feed this chain of computations that normally start with the computation of the cross sections to then compute different steps in the program that need this cross section as the attenuation factor. That is the effect of the matter when the neutrinos travel through the air. Also, you can include the detector effects, like, for example, energy reconstruction efficiency or trigger efficiency, misidentification, etc. So they generate other text files that are finally used to compute the final number of events in order to compare with the data. So at the end, our program takes these input files, generate these output files that you can use for the analysis, and do basically fits, exclusion limits, projections, etc. The nice thing about this procedure is that you start discovering some details of the detector or the machine that you are studying that normally you don't see when you do the approximated computations. Okay, and this is something that I am starting to realize more deeply, and I would like to go forward with that kind of analysis by using, for example, the Andes neutrino detector. So, what is in the last slide? Yes, I would like to just emphasize that as a first step towards doing something that could be useful for the Andes collaboration, for the Andes endeavor, is to use this approach that is very simple to start playing with simulations of these experiments at Andes. And we have enough material to start with this because there are already some papers. There are some papers that are from my advisor, so we have direct communication in order to implement these expressions for the number of neutrinos depending on different properties of the experiment for different situations, different kind of experiments. And the idea is try to systematize that by using a similar approach as we have done for IceCube. However, this is just a first step, I think, because as I have been more involved on this kind of approach to exploit the potential of the experiments, I think that we shouldn't stick to this kind of simple method, and seeing like a way to understand what is going on behind the computations. But in general, it could be possible to use more sophisticated and state-of-the-art tools in terms of cross-sections. For example, there are calculator of cross-sections that include many more detail that our computations of the cross-sections. Also, the detector performances that can be done that can be researched, investigated with Monte Carlo tools, for instance, that go beyond our semi-analytical approach. Or, for instance, more simple than that, it's something that I have just discovered, like doing this kind of, exploring this kind of idea, this kind of tools that already exist in the literature, like Globus, for example, that is a multi-detector simulator. But to be honest, I don't really know exactly what kind of neutrino detector it can simulate and what others cannot. So this is also a way to explore in order to embed what we learned from our particular approach to simulate this experiment in this more systematic approach. But this is something to be done. So just to end, basically, I would like to leave you with this message. So we think that simulations of Andes experiment are going to be important, and we need to work on this. I think this is a nice stage to start thinking about this. What I have realized also with the time exploring this idea is that I'm pretty sure that from the experimental side, for example, people that work in dark matter detectors or neutrino detectors they already work with this kind of simulations. My point of view is more from a phenomenological point of view. Try to see what kind of physics we could look at the Andes experiment and try to work with the simple simulations in order to motivate more research on that direction. That could be done in complementarity with more sophisticated analysis done, for example, by experimentalists or by using more sophisticated programs. So I have said this many times. So this is an idea that I am exploring. I am quite motivated to follow with this approach, and specifically for Andes, but I am pretty open to advices. So with that, I think I am finished. Thank you.
So we have time for a question while we set up for the next speaker. So excuse me, are you next? Are you the next? No. Oh, you're next. Okay, so.
I don't know.
I have already.
Oh, it's uploaded. Okay.
There is one thing in IceCube simulation which is very interesting. Is the ratio between signal to noise for, say, high energy neutrinos. Can you produce this sort of
The ratio of signal to noise?
Yes.
But in which sense exactly?
Well, you take high energy neutrinos, you propose a certain cross section, you calculate the response of the detector, and then you get, an estimation of the background, and then from that you get.
Okay, the background for the high energy neutrinos.
Yeah,
that are
of course.
normally in our in the kind of analysis that we have done, we have analyzed a part of the spectrum that is mostly dominated by astrophysical neutrinos. So the contamination from the atmospheric neutrinos that are the biggest noise for that kind of a signal is quite below. We normally analyze about 200 TB. So normally we neglect that kind of effect. Also, we do that because for practical reason, because in order to simulate the contribution of atmospheric neutrinos, you have to do a bit of more work than what we have done so far. But as we have been focused on high energy, it hasn't been necessary. But now that we are looking at the more at the lower energies in order to do deep core, we're gonna be discussing about that definitely. And this is one of our short-term goals, to analyze this lower energy part.
Okay, so we are a bit behind the schedule, so if there are more questions, you can ask during the coffee break. Let's thank the speaker again.
Thank you.
It's the other way around.
So Next talk is on theoretical calculations of neutrino-nucleus scattering from supernova neutrinos.
Okay, so in this talk I will briefly review some calculations of neutrino cross-section which we have done recently together with a group of Johnny Sonen from Finland and his students. So yes, Osvaldo already talked a lot about the importance of neutrinos as, for instance, from supernovas. I will only briefly summarize. So neutrino-nucleus interactions are very important in supernova explosions and for the creation of heavy elements, and supernova neutrinos can also be used to probe supernova mechanisms which still are partly not clearly known, but also to probe neutrino physics beyond the standard models, because neutrinos in supernova can be affected both by neutrino matter conversions, but also they are the only environment where one can have this kind of neutrino-neutrino interactions, so-called collective neutrino oscillations. And also it has been realized more recently that in the next generation dark matter detectors, which will be even more sensitive, especially coherent neutrino scatterings with neutrinos from astrophysical origins, could actually be a background, create a background events which could limit the discovery potential. So it's important to understand better these reactions. Also, neutrino-nucleus scatterings with neutrinos could in principle be used to study some intermediate states involved in the double beta decays. It has, for instance, been proposed to create beta beams, but so far I think they have not been realized yet. But in principle, one could artificially create neutrinos and then study nuclear structure. So simply the reactions we are interested in are of three types. One is so-called neutral current reactions, which means that we start with the ground state of the nucleus, and then after reactions we end up with excited states, or no excitation is done, so we have elastic scattering. The other, typically for supernova neutrinos, one ends up here with 1+ states. Additionally, we can have short current reactions, which are in principle inverse beta decays. So typically with neutrinos we end up with gamma-Teller or Fermi transitions. However, these transitions are not usually not possible, at least for heavy nuclei with antineutrinos, so therefore one has a bunch of other multiples like 1- and 2- transitions. So from a theoretical point of view, we do so-called state-by-state calculations. So basically one computes from this formula the contribution from each nuclear states and add up everything to get the total differential cross-section, and from that you can obtain also the cross-section by integrating. Typically, from a nuclear structure perspective, what enters are nuclear matrix elements of some operators, and that low energy is typically the same which occurs in beta decays, so Fermi type and gamma type and also with spin dipole type. However, experimentally, one can usually not obtain the cross-section directly, but instead and the number of events from which one can obtain this average cross-section. So typically what we do is to fold the cross-section with some spectra. For instance, for supernova neutrinos, it's of a Fermi-Dirac type, but it's not very well known actually. So what enters the calculations are when some nuclear states, and we need some models to describe them. And since for supernova neutrinos we can have quite high excitations, we use usually the quasi-particle phonon approximation, random phase approximation, which are basically vibrational states created by couple quasi-particle two pairs, either in the neutral version or in the proton neutron version for the charge carrying scattering. And when to treat the odd mass nuclei, we couple these phonons to another quasi-particles, and then we can describe odd nuclei. Okay, so first results I will discuss are for 136 xenon, which is interesting because it's used by a number of double beta decay experiments, for instance the EXO, where we are looking for neutrinoless double beta decays. And it has been proposed to build a new generation detector which will be of a size 1 to 10 tons. And this could then be used also to study, for instance, neutrinos from supernova or from the sun, for instance. And one advantage with this nucleus is that it has a low Q value for charge current neutrino scattering and a relatively large low energy nuclear response, which means that it could be interesting for study, for instance, solar neutrinos. Okay, so here I only show a typical figure of the distributions of the different multiple channels. So typically what one has is 1 plus transitions and 0 plus transitions, and this is what one has for all kind of nuclear targets except for very light nuclei. There is some importance also of spin dipole types, the 2 minus and 2 plus states, because the supernova neutrinos has a continuous spectrum, so one has contributions also from quite high energies. If we go instead to the antineutrino scattering with 1 plus and 0 plus transitions are to a large extent blocked, because with the number of neutrons is quite large compared to the number of protons in this nucleus. And then the spin dipole type of transitions, so 1 minus and 2 minus and so on, are more important. What we also can do is when to compute the number of events at a given radius to a supernova explosion. And what we have to include here is also neutrino mixing according to some mixing scheme. So and here, so with our so when spectra we end up is when a combination of the ones for electron neutrinos and for either muon or tau neutrinos or a mix of them. So this P is their probability. And here to the left I show a result for neutrinos and for antineutrinos. Of course here these results are quite sensitive to what kind of scenario one is assuming for this mixing, which is not very well known for a moment. So this is only an example of how it can look. But one can see that probably with a detector of a few kilotons, one will see at least a number of events per year in the detector. And the cross section for antineutrinos are much smaller, so then the neutral current scattering will be more important. So another study we have done is for 129 xenon, where we computed the coherent neutrino scattering. And here I show a differential cross section as a function of the recoil energy, because since in this case we don't have any transition to any excited state, so therefore we need to detect very small nuclear recoils of order of kVs. So and unfortunately for where cross sections are large, the recoils are very small. But at least if one has a sensitivity to down to a few kV, it should probably be possible to detect this. And this reaction was actually detected for another nucleus quite recently, so it's possible. And as I already mentioned, it's possible in the future that we can have some events in dark matter detectors, so everyone could use them to also study, for instance, astrophysical neutrinos, or it can also create a background which is important to understand. Okay, so here now for the incoherent scattering, so the neutral scattering to excited state for 129 xenon. I compare the incoherent and coherent cross sections. As one can see here, the incoherent cross section is much smaller, and this obviously this is a much more complicated calculations for odd nucleus with a lot of possible final states. And more recently we have studied more systematically all the stable xenon isotopes, and I show a summary of the results here. Here are many numbers, but some conclusions one can draw is that the neutrino cross sections increase with increasing n minus c, which is what is expected, and the opposite trend is seen for antineutrinos, as is seen here. And for odd mass nuclei, for instance 129 xenon and 131, for some reason the cross sections are larger than for the even ones, and this is one fact which is a bit puzzling, which we have not understood clearly yet, but it could be, for instance, due to the fact that the odd mass isotopes has smaller Q values, for instance, and they also have a much more low-lying states, because typically for the even ones you need to excite to quite high lying states. Of course, the odd mass nuclei has also a non-zero spin, so there are much more channels for this which contributes to the cross sections. It should be noticed that the cross sections are quite sensitive to the adapted neutrino mixing scenario, and also to whether we assume normal or inverter hierarchy. So in principle one could use this kind of reactions to maybe test different scenarios for neutrino matching. Once it exists, of course, also experimental results. So lastly, it's important to understand how sensitive cross sections are to the nuclear structure of a nuclear interaction. So therefore, for 116 cadmium, we did a more systematic study using germ forces, because the global properties of cross sections are important to understand for astrophysical applications, for instance, supernova simulations. And in this calculation, we start with a Hartree-Foch-Guillebeau calculation, do similar P and QRP on top of that in a large basis, and we consider then 9 different functionals. And results are shown in this figure, and one can see that there is a quite large variation of the cross sections, but basically one has 3 different cases. One to say that there are some functionals in which gives quite large cross sections, and then there are some which gives in the middle, and then there are the ones which give quite small cross sections. And in the other calculations, we have used also a bond interaction where we fit it to reproduce the gamma-motellar giant resonances. And then we obtain results in principle in the middle here. And some conclusions we can draw is that is, as I said, a quite large variation in the cross sections. And one can actually point with discrepancies to how well the interactions reproduce the gamma-motellar strength. For instance, the variation in the computed gamma-motellar, the position of the computed giant gamma-motellar resonance varies here from with roughly 5 MeVs. And unfortunately, for these functionals usually are fitted to reproduce ground state properties like binding energies and so on, but it's not so easy to fit them to gamma-motellar distributions. There are such attempts, but it's not the single parameter which one can fit. So probably there needs more work in this direction to have reliable results with these functionals if I should use for more global calculations. So now I come to my conclusions. So knowledge about neutrino cross sections for supernova and other neutrinos are important for the detection of neutrinos and the interpretation of future experiments like Andes or other experiments. And actually it would be interesting to use 146 xenon or natural xenon, which is used by many double beta decay experiments, also to study astrophysical neutrinos, but there are of course other options also. And coherent neutrino scattering to be used to study supernova neutrinos, but it requires that we can measure very small nuclear recalls, which only has been possible very recently. And as I mentioned, the next generation dark matter detectors will have a even higher sensitivity, and maybe it's not very well known yet, but maybe coherent neutrino scattering could provide a background which is important to understand so that not the discovery potential is harmed too much, because actually, as I understand, the spectra produced by these reactions are quite similarly also to the ones by certain dark matter candidates. Okay, thank you for your attention.
We have time for some questions.
So this is more of a comment, but
Yeah.
the last bullet you have is not a maybe. This is for sure.
No,
dark matter
I mean,
detections
this
will
is
reach-
some, I think it's a question which, I mean, it has been an interest from the dark matter community to study this, because they are a bit worried about that maybe it could provide a background, but of course there are not so many results. I mean, clearly, I mean, you depending on how large your detector is, if you build a large detector, you can have some scatterings
So
in your detector material.
So I'm saying we are there. I
yes.
mean, for xenon 1
Oh,
ton, we are
okay,
almost
okay.
there, and xenon n ton for sure will reach
Okay,
the
sorry,
neutrino
I
flow.
misunderstood your
So
question.
this is a for sure thing. This is not a
Okay,
maybe we will need
okay,
that.
I'm not an expert on dark
Yeah,
matter.
so I'm
I
saying
was-
this is something that for sure we will need to better
Yes,
understand.
this
This
is-
will
we
produce a
are-
background for us.
We are actually working together with, I think, some group dark matter experiment to study this. But this is, we only have very preliminary results. But yes, it's interesting that you say that we already are there.
Thanks.
Another question? Okay, let's thank the speaker again.
Ah,
Oh, sorry.
Coherence scattering is also large.
Huh?
The difference you showed was for the whole total cross section. In coherence scattering, you also have
Yes, I mean, typically, actually, for the average cross section, the discrepancies usually are smaller than in the cross section, because you integrate, and then usually some of these, discrepancies are averaged out. So probably the problem is even larger for the plane cross section. So. Yeah, so this is a problem, of course. Of course, one problem which I did not mention is that actually it does not exist that many experimental results on cross-section, neutrino cross-section for supernova neutrino energies. There are only some nuclei, so of course. This is something which maybe should be studied even more. But I think it's mostly related to how well you can reproduce this most important nuclear states of these giant resonances. And if you don't, if you fit to that, usually you obtain similar results. But if you want to do a more global calculation, for instance, some people want to do a global calculation for supernova simulations to know a cross-section for a large range of nuclei, then maybe you cannot fit all nuclei. So in that case, you have maybe to be more careful with that, I think.
More questions? Okay, now let's thank the speaker again. It's Felix, Desposorio. So you can switch with him. Thanks. Okay, so next speaker is Felix Desposorio on the quantum decoherence CPT violation at DUNE. Is it okay?
Okay. Good afternoon, everyone. First, thank you for the opportunity. Let's talk about quantum decoherence and CPT violation at DUNE. Well, this work is being done in collaboration with Juan Carlos Carrasco and Alberto Gago. Well, I have divided this presentation in this part, introduction, and here I will talk about a little of neutrinos and the importance of neutrinos to search for new physics. Quantum decoherence, I will explain that we consider the neutrino like an open quantum system that interact with the environment, and due to this interaction, the neutrino lose coherence and this can alter the oscillation probability. And we found here some scenarios that can violate CPT symmetry. And all of this, we work in the context of the DUNE experiment, and well, and all of this is in the context of DUNE experiment. So here I will explain about DUNE. So, about DUNE experiment, and I will give you some simulation details. I will explain how to simulate DUNE experiment, and finally I will give you some preliminary results and conclusions. Well, neutrinos are the most promising window to the new physics. They are very interesting. We know that we have 3 types of neutrinos. We know that they are the second most abundant particle in the universe, and they are almost don't interact with matter. For instance, for each neutrino that interact with an electron, there are 100 million of electrons that interact with other electrons. We have also the neutrino oscillation phenomenon. This is the only solid evidence of physics beyond the standard model. So this oscillation phenomenon happens because the mass eigenstates are different than the flavor eigenstates. So this oscillation, this phenomenon is governed by some parameters that we call oscillation parameters. And these parameters have been measured with a high accuracy in many experiments. However, we still have some open questions that mass hierarchy, that they are fake, so CP violation, and parameter degeneracy. So it means that one parameter can take 2 values and give us the same probability. And moreover, in this oscillation, in this phenomenon, can be manifested new physics, like subleading effects. For example, neutrino decay, non-standard interaction, quantum decoherence, and others. So in order to observe or test this new physics, and in order to figure out these open questions, we need a huge experiment with a high sensitivity, like DUNE. Well, I will talk about DUNE in a few minutes, but now let's talk about something else. Well, by the 50s, we believed that parity was respected. I mean, we believe the naturally expected parity. However, in 1956, Lee and Yang realized that parity was not tested in weak interaction. 1 year later, Wu demonstrated that parity is violated for weak interaction. So we said parity is violated because parity belongs, or parity is part of a larger symmetry that we call CP, charge parity. And we said that charge parity had to be respected. But in 1964, CP violation was demonstrated. So we said the same. We said that CP is violated because CP is part of the larger symmetry that we call CPT. So what is CPT in neutrino oscillation? Is our theory of neutrino oscillation respect this symmetry, respect CPT. We have to fulfill this expression. So the probability of nu alpha going to nu beta have to be equal to the probability of nu beta bar going to nu alpha bar. Well, here in this work, we found some cases, some scenarios that don't respect this symmetry. And we are studying the possibility to measure this CPT violation at DUNE experiment. So now let's talk about quantum decoherence. Here we consider a neutrino like a quantum system, an open quantum system that interacts with the environment. And due to this interaction, the neutrino lose quantum coherence. And so the interference between the mass eigenstate can be altered. And as a consequence of this, the oscillation probabilities can be altered too. So the time evolution of this system, of this open quantum system, is given by this expression. This is the Liebland equation. This is the density matrix, the Hamiltonian, and this term describes the decoherence. So the most general expression for this term is this, where this operator have to be Hermitian and depends on the number of the generation of neutrinos. So if we consider 3 generations, we have this expression for probability. Probability of nu alpha going to nu beta depends of rho, and this depends on the standard oscillation parameters, and m depend of the Hamiltonian and the dissipative factor. I have to mention here, if we have to calculate the probability for antineutrino, we have to consider here rho bar, h bar, but we have to consider the same dissipative factor. I mean, we are considering here the same dissipative factor for neutrinos and for antineutrinos. This is very important. Now, the expression for rho, we have this expression for rho. Here we can notice that we have 3 imaginary elements and 5 real elements. So if we combine one real element with one imaginary element, we can obtain here a term that don't respect CPT symmetry. So in a CPT violation case, one coefficient of this factor must be imaginary, or I mean rho 2, 5, or 7, and the other should be a real 1, 3, 4, 6, or 8. Having in total 15 cases. We use the difference of survival probability to refer CPT violation. So if we don't have CPT violation, this must be 0. And we consider the following. All the diagonal elements of the dissipative matrix are equal to gamma. So we consider the all diagonal elements of D of our dissipative matrix equal to gamma. And we consider the same dissipative matrix for neutrinos and for antineutrinos. And the dissipative matrix is containing only just one no diagonal elements at a time. So with this consideration, we have this expression for the CPT symmetry. This is the no diagonal elements that are related with this rho, and this is the damping term. So now we study the impact of the 15 cases of CPT asymmetry. We consider the nu-mu and nu-mu bar disappearance channels in the context of DUNE, and this relation between the no diagonal element with gamma, the diagonal element. Here we have the asymmetry, CPT asymmetry, and the energy. And we set the value for the decoherence parameter in 10 to minus 23 GeV. So here we can notice the behavior of ACPT, the symmetry CPT, for beta 1, 2, beta 4, 5 for the red line, and 6, 7 for the blue line. And now we choose this value because we have the maximum amplitude when delta CP take this value. We can see this in this slide. Here we have the delta CP and the coherence parameter, and this is the CPT asymmetry. We can notice here that we have the maximum asymmetry when delta CP is 0.5 and 1.5. We can notice here the damping effect. The CPT asymmetry grows with gamma and until the maximum point, and then decrease. We studied also the energy dependency. We consider this energy dependency in this way, minus 1, 0, 1, and 2. And we realized that the energy dependency change the value of gamma for the maximum asymmetry, but keeps the amplitude. It keeps the same. So all of this information, we work with all of this information in the DUNE experiment, in the framework of DUNE experiment, and let's talk about DUNE experiment now. And this experiment will be running in 2026, and is located in the United States. And how it will work? Well, they will accelerate a proton beam, and this proton beam will collide with a target. And as a consequence of this, we will obtain pions or kaons. They will be focused with magnetic fields, and here they will decay in muons and neutrinos. We separate the neutrinos from the muons, and we have finally our neutrino beam. Our neutrino beam will travel through the Earth 1,300 kilometers, and finally they will be detected with liquid argon, 40 kilotons of liquid argon. And we simulate this experiment using GLOB software and using the ancillary files of the DUNE collaboration. In order to show tangible results, we define this observable CPT asymmetry that depends on the number of events, the difference between the number of neutrino and antineutrino muon. However, we have a fake CPT symmetry due to the matter effect. So in order to differentiate the CPT violation due to the effect of quantum decoherence and CPT violation due to the matter effect, we define this ratio. Here, we consider the matter effect and the coherent effect, and here we just consider the matter effect. So we have these results. We build this configuration for the dissipative term that can give us a very big impact in CPT violation. And we realize here that we have the maximum impact when delta CP is 1.5. And we consider here all the events between the 0.5 and 20 GeV for 5 years in neutrino mode and 5 years for antineutrino mode in normal hierarchy. With this information, we made this analysis. This is the ratio, and this is the coherence parameter. And the dashed line represents the standard oscillation. I mean, if we don't have CPT violation due to quantum decoherence, the solid black line must be equal to the dashed line. So we have here some error bars for 1 sigma, 3 sigma, and 5 sigma. Here we found 5 sigma of confidence when gamma is equal to 4 times 10 to minus 23 GeV. And we do the same for all the energy dependencies. Well, the conclusions, we revisit the theoretical framework of quantum decoherence phenomenon in the context of the neutrino system. And when we consider 3 flavors, we identify 15 parameters of the decoherence matrix that produce a violation of CPT symmetry. We develop an analytical expression for probability and CPT asymmetry in vacuum, and we use the channels nu-mu and nu-mu bar disappearance to analyze CPT asymmetry. And its dependence on gamma, delta CP, and energy. And finally, we found a high impact in CPT asymmetry when we consider this value for delta CP and normal hierarchy. And in the context of DUNE, we found 5 sigma of confidence when gamma in this order is equal to 12.1, 4, 1.7, and 0.7 for this energy dependency, -1, 0, 1, and 2, respectively. Well, that's it. Thank you for your attention.
So for the dissipative term, is there a first principle physics that determine that it has to be the same for neutrino and antineutrino, or this is just an assumption?
Sorry, could you repeat, please?
Yeah, for the dissipative term, you assume it is the same for neutrino and antineutrino.
Yes, the
right?
same, the same.
Is there any underlying physics that determines that it is the same, or is this just an assumption?
This is our hypothesis. Okay, we can obtain CPT violation considering different dissipative terms for neutrino and for antineutrino. This is another way to obtain CPT violation, but this is our hypothesis.
Okay, thanks.
I mean, there was the same question, but you have already answered it. The other question is, That's expression for the A, which is square root of delta square, and so on.
This.
Yeah. So that is based on the three. So you're taking there the three flavors and the three mass eigenstates.
Yeah, because with two flavors we don't have a CPT violation.
Yeah,
with this,
that
yeah.
was
Yeah.
So you don't have that for the absolutely. Yeah, yeah. Okay, that was the main question. But then, almost for technical purposes, I mean, we are working in the coherence, but for neutrinos coming from supernovas, and we are not using Liebman equation. Simply, we work out in a Hamiltonian frame by assuming a certain structure for the environment, and that's it. So the full Hamiltonian is decomposed in the flavor Hamiltonian, the matter Hamiltonian, which is taking account the interactions with matter. We are changing the composition of the mixing angles and so on, MSW effect. But then the interaction with the background is just, I mean, the interactions with the remaining neutrinos which are moving around. And the formalism is completely Hamiltonian. I mean, you don't have any complications like dissipative term. So.
Well, this is the typical way to solve the time evolution of the open quantum system. I didn't know about the other way. But
it's called, I mean, the spin model for decoherence.
Oh,
and
that's interesting. But I didn't know. I will.
So and then the main so you view the same effects here because in that treatment what you do is you follow the time evolution of the components of the density matrix until you get the zero in the non-diagonal elements. So then from the pure state you come out with a mixed state. And so but it's essentially the same.
Yeah, it must be.
But much more easier to compute.
Must be. I have to review about.
Okay, good. Thank you.
Thank you.
It's a question of my confusion here. I don't see where in your formulation is the CPT, non-conservation coming, and what parameters? Is this raw parameters or something?
Here, yes, these raw parameters. If we combine a real element with an imaginary element, we can obtain here a term that don't respect CPT.
Okay. So this is just simply parameters. You don't have a fundamental theory what this should happen, or
no, we figure out, we realize about it, but we don't have as you said a fundamental theory for this.
Yeah, and it's not the interaction with the medium or something, or what?
Sorry, what?
Well, I mean, you could have this difference of the antineutrino A to B compared to the neutrino B to A could be different because there's an interaction with the medium as if they propagate something.
This is we call the fake CPT asymmetry.
Right.
That is why we use this ratio, because there is because the neutrino and antineutrino interact in a different way with the matter.
Of course.
Yes. Yes. In order to differentiate, we define this ratio.
Okay.
We consider this. Yeah.
All right. Thank you.
More questions? Okay, so we can go to the coffee break and we'll be back in 20 minutes. Thanks.
You're sending a 40 kilogram liquid argon detector?
Yeah, the same. This is the configuration by default that you
I know. I was not just not sure that it is fully finalized, that all 4 modules will be liquid argon single phase DCs.
Excuse me.